Hey geometers, welcome back. In this video lesson, we are going to talk a little bit more about triangle congruence, the theorems and the postulates. This is pretty much all of chapter 5, or the rest of chapter 5. So here we go. So we need to review a little bit of section 5.2. And remember that our lesson looked a little bit something like this. We talked about congruent polygons. And in that lesson, we defined how do we know if two polygons are congruent? And the definition, the geometric definition, is that two polygons are congruent if and only if there's rigid motion or a composition of rigid motion that maps one figure onto the other. And remember, we looked at that really cool GeoGebra applet where you could slide. There's actually a video of the applet where you had the little slider and it showed how a translation and a rotation or a translation and a reflection or something like that mapped one congruent figure onto another. Okay, so the result of having two congruent polygons, okay, is that they're the same size and shape. So these are congruent, these are not congruent. And then specifically, we're going to look at triangles for the rest of this chapter and the rest of this lesson. Okay, and so when we looked at two triangles that are congruent, we know that all 6 corresponding parts are congruent as well. All 3 angles of one triangle and all 3 corresponding parts of the other triangle are congruent, and all 3 sides of one triangle and the 3 corresponding sides of the other triangle are congruent. So having those 6 parts that's actually a result of congruence. And we also talked about being very specific about how we name the congruent shapes, right? So if we know that these 2 triangles are congruent, okay, we have to be very careful, very precise with lining up the vertices in the correct spot. And I showed you a shortcut for visual learners. You can look at these complex diagrams and kind of match them up visually. Okay, for those of you that are non-visual learners or not as strong with their visual learning, okay, you can just look at this statement right here, and that tells you everything you need to know. All the corresponding parts are there. The vertexes are there, or the angles. J matches with T because it's in the first spot. K, S, L, R. Okay, second spot, third spot, third spot. Also, the sides are there. Side JK, okay, the first 2 letters matches with side TS. Okay, side KL matches with side SR, and side JL matches with side TR. Okay, so these statements, these congruent statements, tell you a lot of information. You can figure out all 6 of the corresponding parts just from this statement. Or for strong visual learners, you can just parse this visually, this diagram visually. You can match it up with your eyes. Okay. So this is really fundamental to the rest of this chapter and this entire lesson. We culminated our lesson in 5.2 with doing a proof. Okay, and to prove that 2 triangles are congruent, we had to show that all 6 parts of one triangle are congruent to all 6 corresponding parts of another triangle. And then finally, we could conclude that yes, those triangles are indeed congruent. Okay, so here's all 3 sides, and then here's all 3 angles. Okay, so those are all 6 parts. Okay, so now in this lesson, instead of going through all 6 parts, we're going to go through 5 theorems. The book calls them theorems. Some other textbooks call them postulates. Some authors actually call them a combination. Some of them theorems, some of them postulates. I'm just going to call them theorems because that's what our author calls them. Okay, and it doesn't matter whether they're theorems or postulates. We're going to use them all. Okay, so there's 5 shortcuts that we're going to use. These are the triangle congruence theorems. Okay, there's 5 shortcuts or triangle congruence theorems. So when we're trying to prove that 2 triangles or show that 2 triangles are congruent, we're going to hopefully use one of these 5 shortcuts. So here they are. I'm just going to tell you what all of them are first, and then we'll go through them one at a time. And we'll go through an example of a proof for every single one. And I even threw in a couple examples for you guys to just kind of work on. Okay, so here they are. It's SAS, which stands for side, angle, side. SSS, side, 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 AAS, angle, angle, side, and ASA, angle, side, angle. This fifth one is it's kind of a special case, so it doesn't really come up that much. It only pertains to if you're trying to prove that two right triangles, are congruent, and it is called the HL, or hypotenuse leg theorem. Okay. So the way that these things work is the order is very important. So if it's SAS, okay, notice the A is between the two S's, okay, and that is what it's going to have to look like in the diagram. This angle is what's called the included angle between these two sides. Okay, so it's a side, then a very next angle. Okay, so this side makes up part of this angle, and then the very next side. Okay, side, 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 order doesn't matter. AAS and ASA, yes, order matters. Okay, and some students get a little bit confused looking at the diagram, whether it's actually an AAS or whether it's a case of ASA. Okay, the big difference is that with ASA, the side is the included side. It's the side that's right between the two angles. Okay, versus this, the side is not between the two angles. Okay, I'll show you what I mean when we get to that example. So let's start with the very first case, SAS. Okay, so let me just throw the theorem up here. This is what it says. Okay, I'll read through it in a moment, but first let's just kind of visually digest this diagram. Okay, so in this diagram, we have two triangles just kind of sitting there, minding their own business. And we notice that those two triangles look to have a lot of common traits, right? Now, we don't know for sure. We're not given by this diagram whether all 6 parts of this triangle are congruent to all 6 parts of this triangle. We don't need all 6 parts, right? So all we're looking for are 3 parts, 3 very specific parts, and we have those. Here we have a side with 1 congruence mark, so that matches with this side with 1 congruence mark. Here we have an angle, okay, with 1 congruence mark. That matches with this angle that has 1 angle congruence mark. And then here we have another side with 2 side congruence marks, and that matches with this side that has 2 congruence marks. Okay, so we have a case of side, angle, side. Notice that the angle is the included angle, meaning it's right between the two sides. Literally, these two sides make up the sides of the angle. Okay, so let's read the theorem. So if two sides and the included angle, so what does included mean? It means it's right here. It's the angle that's right between the two sides. Okay, so if two sides and the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. Okay, so this is what it's going to look like. Okay, notice this statement. Okay, let's talk about this statement. Triangle ABC is congruent to triangle DEF. Okay, what if we were being a little bit hasty and we wrote something like, oh, triangle ABC is congruent to triangle FED? Okay, would that be correct? No, it would not. Okay, ABC has to match with the corresponding parts. Okay, so A has 1 congruence mark, so it matches with D because it has 1 congruence mark. So first position, first position. B, we just happen to choose B in this triangle. We could have gone ACB, but we went ABC. So B, how do you know that matches with E? So strong visual learners, you can see this with your eyes. You can see that if you were to just flip this or reflect it and then rotate it a little bit and translate it, they would map onto each other. Okay. If you're not able to see that, that's okay. Okay. When you look at B and you look at E, okay, look at the sides. Side AB is side from A to B. So it has this 1 congruence mark. So it has to match with the side that has this 1 congruence mark. And we already know that A matches with D. So AB matches with DE. That's how we know that B matches with E. Okay, and then by the same reasoning, C would match with F. So AC has 2 congruence marks. DF has 2 congruence marks. Okay. All right, so let's go ahead and use SAS in a proof. Okay, so we have a diagram that looks like this. Okay, and we're given a couple things. First of all, there's a congruence mark right here and a congruence mark right there. So we know that those two sides are congruent. Okay. Now, this diagram is a complex diagram. Why? Because you have sort of overlapping triangles. Okay. So strong visual learners, you can do some you can sort of parse this with your eyes. You can sort of pull this, take this diagram apart with your eyes and match up the corresponding parts with your eyes. If you're not able to do that, then you need to redraw the diagram. Yeah, redraw the diagram, and really all you have to do is this triangle that's sitting on top, you just rotate it around and draw it down here so it's sort of sitting in the same orientation. Be careful when you redraw the diagram. I have one example of redrawing a diagram later on in this lesson. But when you redraw the diagram, make sure you also redraw the given congruence marks. Okay. So here we're only given one congruence piece. Okay, but we're also given this right here. What does that mean? Parallel. We're given that side BC is parallel to segment AD. Segment BC and segment AD are parallel. Okay, so now we have, if you ignore this side and ignore this side, then you just have two parallel lines cut by a transversal. And anytime you have two parallel lines cut by a transversal, well, we know that alternate interior angles are congruent. Okay, so there's a couple ways to go about this proof. Okay, so let's first go ahead and identify alternate interior angles. So this angle right here, angle BCA, is congruent to angle DAC. DAC, this angle. So these two are alternate interior angles. So now we have two pieces. We have a side and an angle. Okay. Well, what about this side right here? That is a shared or common side, and it is congruent to itself. Will it map on top of itself? It's already mapped on top of itself. Okay, so we know that segment AC is congruent to segment CA. Okay, and I explained in the last video why you have to say that segment AC is congruent to segment CA instead of segment AC is congruent to segment AC. That would be wrong for the purposes of this particular proof. Why is that? Because in this proof, we have to match up the corresponding parts. Okay, so when I'm looking at segment AC for this bottom triangle, okay, well, vertex A actually matches with vertex C in this top triangle. That's why segment AC matches with segment CA. So finally, you can see that I have a side, an angle, and a side. And the angle is the included angle. So now we can finally conclude that those two triangles, the triangle on top and the triangle on the bottom, are indeed congruent by the SAS congruence theorem. Now I'm fine if you just write capital S, capital A, capital S. Okay, every teacher, every geometry teacher will accept that. You do not have to write out congruence theorem. Okay. Okay. And just be very careful in statement number 5 that you match the correct corresponding vertices and sides. Okay. So triangle ABC. So if we're naming this top triangle, triangle ABC, okay, well, on the bottom triangle, which vertex matches with A? It's actually vertex C. Okay, and then if we're going to B, then from here we're going down to D, and then we're going to A. So it's triangle CDA. Okay, our next congruence theorem is side, side, side. This is the easiest one. This is a super easy diagram to just kind of visually digest. Okay, you're going to see one congruence mark, 2, 2, 3, and 3. All three sides of one triangle are congruent to all three sides of another triangle. Those two triangles are indeed congruent. All right, so let's go ahead and use a proof or do a proof using the SSS. Okay, so here we're given two triangles that are kind of stuck on top of each other or stuck next to each other. Okay, and this triangle on the left, we have one congruence mark, two congruence mark. Here we have one congruence mark, two congruence mark. Look for a shared side. Do we have a shared side? Yes, we do. LM is a common segment. LM is a common side, right? It's a common side to both of those triangles. So we're going to say that segment LM is congruent to segment MLM. Now, how come we didn't have to say segment LM is congruent to segment ML? Think about that for a moment. Clue, look at where the 1 and the 1 are. Look at where the 2 and the 2 are. Okay, so hopefully you figured out why this is the correct statement. And now, okay, now if I was actually doing this proof, you should be marking this diagram as you go. Okay, now I'm not able to write on my screen. I don't have that kind of screen. I'm using my MacBook Pro. Okay, so I'm not able to write, but you would just make 1, 2, 3 congruence marks on this segment. Why 3? Because 1 is taken up here, 2 is taken up here, and then 3 means that these two segments are congruent to each other, but they're not necessarily congruent to this segment or that segment. Okay, so we are done with our proof. Triangle KLM congruent to triangle NLM by SSS. All right, so let's check for understanding. Okay, are these congruent statements true or false? So be very careful. Okay, be very careful when you're evaluating these statements. Okay. So what are we looking for in this type of problem? Well, what we're looking for is, first of all, are the two triangles congruent? And yes, they are, because we can see we have side, side, side. So these are congruent by SSS. But the tricky part is the statement correct? Are these in the correct order? So this triangle, they decided to call it DFG. Okay, and does that match with HJK? Does D match with H? Well, yes, it does. How do we know? Because D is the angle that is formed by the two sides that have one congruence mark and two congruence mark. One congruence mark, two congruence mark. So D does match with H. What about F? Does it match with J? Yes, it does. 2 and 3, 2 and 3. And then does G match with K? Well, it has to. It's the last vertex. So this one is true. Here's another example. Okay, a little bit more complex. This one was a softball. This was hopefully this one was easy because these two triangles are just sitting in the same orientation. But you're going to have more complex diagrams, things that are like this and even more complex than this. Okay, and I'll show you some examples. Okay, but check this out. Strong visual learners, you can see that this is really just a reflection, right? The rigid motion that would map one figure onto the other is simply a reflection. Okay. And is this the correct statement? So again, we have SSS. Is this the correct statement? Does Q match with R? Q is the very obtuse angle. That's between 1 and 3. R is the very obtuse angle between 1 and 2. I think I said 3. I meant 2. Okay, so that is correct. P is this very sharp, very acute angle up here. S is very sharp and acute. 2 and 3, 2 and 3. Yeah, we're good. So that is also true. Okay, let's move on to the HL, hypotenuse leg. Hypotenuse leg only works when you're working with two right triangles, okay, two or more right triangles. So hypotenuse leg. So this basically tells us that if you have two right triangles, all you need to know, instead of knowing three things, okay, like SSS and SAS, you only need to know two things. If you simply know that the hypotenuse and the leg, and either one of the legs, it doesn't matter. And by the way, when you're looking at a right triangle, okay, the hypotenuse, if I'm looking at this triangle ABC, it's a right triangle, I can see there's a right angle. How do I know where the hypotenuse is? Yeah, hopefully you remember that the hypotenuse is the side. First of all, it's the longest side, but it's also the side that is opposite from the largest angle, which is the 90-degree angle. Okay, so this is the hypotenuse because it's opposite or across from the right angle. Okay, all right, and these two other sides are called legs. Okay, remember the lesson we learned about base angles? Okay, there's the base, one side is called the base, and the two other sides, the two congruent sides, are called the legs. Yeah, it's kind of like that. Okay, in a right triangle, one side is called the hypotenuse, and then the other two sides that are not the hypotenuse are called the legs. Okay, so HL tells us if you have two right triangles and we know that the hypotenuse is congruent to the hypotenuse, and either one of these legs is congruent to either one of these legs, that's enough to conclude that those two triangles are congruent. Okay. Now, if you think about this, okay, this is it's kind of like you only need two things, but sneakily, we actually really have three things, don't we? Because we have this right angle, right angle. We know that all right angles are congruent. In fact, I think there's a postulate that says all right angles are congruent. Okay, so we actually have three things, don't we? All right, so let's go ahead and use HL. So in HL, you're going to have a diagram. And this is a very complex diagram now. Okay, but luckily they've given us a proof statement. Okay, so the proof statement is prove that WYZ, triangle WYZ, so WYZ, so it's this triangle that's on this left side of this overlapping, I don't know, fortune cookie or whatever it looks like. Okay, is that congruent, or prove that that's congruent to triangle XYZ? XYZ. Okay. So, one strategy, again, if you're struggling with these overlapping complex diagrams, just simply redraw the diagram and pull those two triangles apart. Okay. So, we're given three things. So, I haven't done this in this diagram. Again, I can't draw on this screen, but you should, in your notes, make these marks. Okay. The first mark you're going to make is that segment WY is congruent to segment XZ. So WY is this long piece right here, the entire piece. So I would put one congruence mark right here. And that is congruent to XZ, segment XZ. So I'd put a congruence mark right there. Now I'm also given that segment WZ is perpendicular to Z. So WZ is perpendicular. So I would go ahead and make a little box, the right angle symbol right there. And then likewise, the right angle symbol right there. Okay. So I am given two right triangles, and I know that the hypotenuse is congruent to the other hypotenuse. I'm given that, okay? So all I need is a leg, and I can use hypotenuse leg. Well, look for shared or common sides. Do you see any shared or common sides? Yes, you do. This bottom piece right here, side ZY, is congruent to side YZ. Okay, so now you have hypotenuse leg. So here I'm going to go ahead and show you how I would redraw this diagram. Okay, so here's triangle WZY, okay, or WYZ. This triangle I just redrew right here. And then this triangle, what did I do? I redrew it here, but I also did what? I flipped it, or I reflected it, right? So now it's sitting in the same orientation as this other triangle. Okay, and what did I do? I put congruence marks right here. Why did I use two? I don't know. I probably should have just used one and one. Okay. All right, so here is our nice diagram that we redrew. Here are our givens. Here is the proof statement. Okay, so I put these in two different statements. Okay, these are both your givens. So where do we go from here? Well, we had a shared before we go to the shared side, what can we do? We can say that angle Z and angle Y are right angles. Okay. Why do we have to say this? Because this statement, perpendicularity, does not give you congruence. Okay. Perpendicularity can lead to knowing that you have a right angle. Okay. So this is actually two statements that follows from these two statements. Okay, and that is the definition of perpendicular lines. So because I have perpendicular lines, that creates some right angles that I can then identify. Okay, so now I have to say that, well, these are both right triangles. How do I know that? Because they both have right angles in them. Okay, why do I have to make this statement? Because again, I'm going to be using HL, and to use HL, it only works for right triangles. That's a condition that has to be met. So now I'm going to go ahead and use reflexive. Okay, that bottom segment, okay, is congruent to itself. And finally, I'm going to conclude with the HL congruence theorem. Okay, HL congruence theorem. All right, so now here's our last two, I'm going to combine ASA and AAS. I'm going to put them side by side. And the reason I'm doing this is because when I teach them one at a time, sometimes students get a little bit confused. So I found over the years that the best way to help students not be confused is to show both of them side by side and show what the difference really is. So here's ASA, and then here is now AAS, okay? Look at the diagrams. The diagrams will show you everything you need to know about what the difference between ASA and AAS is, okay? With ASA, just look at the letters, the S is right between the two A's, okay? So just like this in the diagram, the S is right between the two A's, right between the two angles. Okay, so the side is the included side. It's the included side. Okay, so it could have been this angle and this angle on this side, or this angle and this angle on this side, but in this case, it's these two angles and the included side. Okay, so this is ASA. AAS is where you have three pieces, two angles and a side, but the side is not right between. Okay. If you ever have a side, if you ever have two angles that are congruent and one side that's congruent, but the side is not the included side, you know that you're dealing with AAS. Okay, so let's go ahead and use ASA to do the world famous bow tie proof. Okay, there's actually many different bow tie proofs. Okay, I just like to call this the bow tie proof because it looks like a bow tie to me. Okay, so let's evaluate this visually. What do we have going on here? So we have two triangles that are adjoined at this vertex B. Okay, so I don't see any shared sides in this, but I do see a shared vertex. Okay, what else are we given? We're given that this piece right here is congruent to this piece. So segment BD congruent to segment BC, but we're also given parallel lines. So when you're given parallel lines, okay, remember that you have AIA, AEA corresponding, and CIA at your disposal. Okay, so you have two parallel lines cut by transversal here. So we know something about alternate interiors. You also have two parallel lines cut by transversal here. So you know something about these alternate interiors. But notice that you also, at this shared vertex of the bow tie, okay, right in the center of the bow tie, at this shared vertex, you also have vertical angles. Remember, I taught you that vertical angles are always congruent no matter where they show up. Okay, and this is one of those classic cases where you have vertical angles right here. All right, so let's go ahead and prove the triangle ABD is congruent to triangle EBC. Okay, so we start with one piece of the givens. We start with the parallel lines. And then we're going to go ahead and use alternate interior angles. And we just went ahead and chose angle D and angle C. You could have used A and E, doesn't matter. But we just went ahead and because I'm trying to use ASA, we just went ahead and used D and C. Okay, so I would mark this in your diagram. Make sure you mark these as you go. Okay, so every time you prove something, mark your diagram. Okay, it will tell you what to do next. So now we're going to go ahead and say that segment BD is congruent to segment BC, and that was given. Notice that you don't always have to front load your proofs with all the givens. Okay, you can kind of use the givens as you need them. Okay, and I've strategically used the given here because see how we have ASA? I'm going to prove this in the order of A, S. What do you think is going to come next? A. There it is. So now I went ahead and used vertical angle theorem, VAT. This angle, ABD, is congruent to this angle, EBC, vertical angles. So now if you've been marking your diagram, you will clearly see congruent, congruent, congruent. It is clearly ASA. So make sure you mark your diagrams. When I see your tests and your quizzes and your homework, Especially when I see your final exam, I better see those marks that you've been marking your diagram as you were doing the proof. All right, now let's show you an example of AAS. AAS, okay? So again, another complex diagram. We have two overlapping triangles, right? This triangle that's sort of on top, we'll call that triangle HFG. And then this triangle that's sort of on the bottom, we'll call it triangle GKH. One thing really nice about proofs is that they tell you exactly, you know exactly what you're headed towards. Okay, so in a way, these proofs are pretty easy because you know exactly like what matches with what or what is supposed to match with what. Okay, we have a couple of givens. Okay, we have parallel lines, and then we also have right angles. All right, so anytime you have parallel lines cut by a transversal, we know that we can just look for alternate interior angles, which we have. So GHF, angle GHF, so this angle and this angle, HGK, those are AIAs. We know that those are congruent. Angle F and angle K are right. Therefore, angle F must be congruent to angle K. That is called the right angles congruence theorem. I'm fine. Now, when you're writing these theorems, okay, like the right angles congruence theorem, theorem 2.3, first of all, don't ever put theorem 2.3. That is arbitrary. That is just based on where there's no actual number theorem 2.3. That is just something that the authors use to keep the theorems organized that we present to you in this Big Ideas textbook. Okay, so don't write theorem 2.3. I don't want to see it. Okay. You can write the name of the theorem like this, right angles congruence theorem. Okay, or you can simply, if you don't remember the name of it, because some theorems the name really doesn't matter, you can actually just write what the theorem says. Okay, so for this, you could just write all right angles are congruent. Okay, that's all you would have to write there. That's how I remember it. That's what I prefer to accept. That's what I prefer you guys to remember. Okay. So finally, we are going to use this common shared side. Segment HG is congruent to segment GH. And then if you've been marking your diagram, as I've taught you to, you will see that what you have is AAS. Okay. How is this AAS? Because we have angle, angle, side. Okay. Or angle, angle, side in this top triangle. Okay, this side is not the included side between the two angles that we proved that are congruent. All right, a couple more examples. Okay, are these two triangles congruent? If so, write a congruent statement and justify with a theorem. So justifying with a theorem is either going to be SSS, SAS, AAS, ASA, or HL. Okay, so first of all, are these two triangles congruent? Pause the video and see if you can figure it out. Okay, hopefully you found that we have a common side. So that would be SAS. So that's a big yes. Okay, SAS. And then make sure that you match the corresponding parts. Okay, this is not the only correct answer. I happen to call this triangle on the bottom left here, I happen to call it triangle GHF. Okay, you might have called it triangle HGF. Okay, or triangle FHG. Okay, well, it doesn't matter. Okay, as long as these three letters match in the same order as these. So if you called this triangle FGH, okay, what would you have to call this triangle? FGH would match with HFE. Okay, all that matters is that the letters correspond to each other. All right, pause the video, see if you can figure out if these two triangles are congruent. If so, write a congruent statement and justify with the theorem. Okay, same thing. This one was a lot easier because the diagram's much more clear. The triangles don't actually overlap each other. Okay, and we already have the three things we need in the correct order, SAS. So this is more just a matter of, can you match the vertices properly? There it is. Triangle ABC, congruent to triangle EDC. All right, a couple more examples for you. Okay. Are these two triangles congruent? What do you think? Hopefully this one was easy for you. You don't even have to pause the video. SSS. So always look for that shared or common side. Okay. This one is probably one of the hardest ones so far, but it harkens back to something we did earlier. One of the proofs I did for you earlier. But see if you can figure this one out. Okay, so we can use HL theorem here. HL theorem. Why? Because this side is a shared side. Okay, it is a shared side. We have two right angles. Okay, so we have right triangles, and then we have AC congruent to BD. So we have hypotenuses, and then we have one leg. So that's HL. All right, this one I think is pretty easy for you. Hopefully you can just recognize this. Okay. You have two angles and a side. Is the side included? Is it right between the two angles? No. So therefore, this is AAS, not ASA. Okay. Here's one that I think we just did a proof on. Okay, does this one work? Actually, there's more than one correct answer for this. There's more than one way to do this one. Okay, there's actually two correct answers. See if you can come up with two different ways to do this one. So the way that we did it in the proof example was AAS, but is there a different way? Yeah, you could also do SAS. How would you do SAS? Well, we have one side here, we have an angle here, and then we have a shared or common side here. We could even do, I guess we could even do another thing, couldn't we? If we did alternate interiors here, oh, that wouldn't work. Okay, alternate interiors are here and here, but not here and there. Okay, yeah. Okay, so here's a summary of your strategies, okay? It may be worthwhile to redraw the diagram, especially if you're struggling to really like visually parse the diagram, okay? If it's hard for you to block out parts of the diagram and that kind of thing, just go ahead and redraw the diagram to the best of your ability. Just be careful when you redraw the diagram, make sure that you also put in all the given information, like all the congruence marks, if there's any right angles, if there's any parallel lines, anything like that. Another strategy is add the congruence marks as you go. So every time you make a statement and you prove that something is congruent, go ahead and add that mark to your diagram. Look for shared or common sides. How many times do we have shared or common sides? Many times. Finally, use the triangle congruence theorems. Use the shortcuts now that you know them. SSS, SAS, AAS, ASA, and HL. All right, guys. Hey, one last question. And by the way, this video serves for all three of these lessons, L65, L67, and L68. Those are all triangle congruence worksheets, okay? By the way, which one of these is your favorite thing to eat? Okay, if you had to eat one of these, you have to eat one of these. Which would you choose? All right, guys. Hope you enjoyed the video. See you in the next one. Thanks.